Okay, so today we're moving on to a topic that will be very familiar to you by the time that you leave this program, and that's the concept of distance measures, which in mathematics are typically called norms. So we'll start with vector norms. Norms are functions which measure the magnitude or the length of a vector. They're commonly used to determine similarities between observations by measuring the distance between them. So why would we want to measure similarities between observations? Well, we might want to find groups of similar observations or customers or products so that we can market to the same customers, or we can market a certain group of products to people who are likely to buy them. Or we might also want to classify new objects into some known groups, and we want to know what group is this new object, most similar to. And it turns out there are many ways to define distance and similarity between vectors and matrices. We're going to talk about just a few of these today. But in general, a norm or a distance metric is any function that's going to take a vector or a couple of vectors as input, and it's going to return at just a scalar quantity, some distance, 4 miles. A vector norm is typically denoted by these two vertical bars surrounding the input vector. And what this does is signify that it's not just any function. A distance function has to satisfy some very specific criteria. And so these are always presented when we talk about norms. We're probably not going to revisit them again, but these are good things to know, and some of them are quite intuitive. So the first one is that if I have a scalar, then the norm of a scalar times a vector x is the same as taking the absolute value of that scalar outside of the norm. I'm sorry, this should be a boldface x right here, so that same vector x. It's also got to satisfy what we call the triangle inequality. So if I take the total magnitude of x plus y, that's got to be less than the sum of the individual magnitudes, x plus y. And one of the ways you can think about this is that the hypotenuse of a triangle can't be bigger than the sum of the two legs of the triangle. That's why it's called triangle inequality. And then these are the really important ones right here. So the length of a vector is 0 only if that vector is equal to 0. So if every element in that vector is equal to 0. And a distance or a length or a magnitude is always going to be greater than 0 for any vector. I can't draw a vector that has a length of -3. And this may be clearer when we actually look at the picture. But the first norm that we're going to talk about is the Euclidean norm. Okay, so this is sometimes called the 2 norm. And all that does is measure the Euclidean length of a vector. And by Euclidean length, we're talking about length how you would measure it with a ruler. Okay, and so the length of a vector is the distance from the origin to the point. So if I have some vector with n elements, call that x, so x is x1 through xn, then the magnitude of x, or the length of x, is the square root sum of squared elements in x. Another way that I can write this is that it's the square root of x transpose x, right? X transpose x gives me the sum of the individual elements squared. This is something that we should already have seen several times by now. Okay, so the 2 norm is just the square root of x transpose x. And part of the reason I give you all this information is that when you go to research things in data science, you don't know who will have written that article or that white paper. And if it's a mathematician, they're going to be talking about the 2 norm or the L2 norm or Euclidean norm. If it's written by someone who's more in the data mining community, they might refer to distance or Euclidean distance or the magnitude. But it's important to have all of this terminology under our belt so that we can read it regardless of who is writing the source. And so with these 2 vertical bars, when you see 2 vertical bars and they don't have this little 2 here to specify the 2 norm, that's what they're talking about. They are talking about the 2 norm. Okay, so this is by far the most commonly used norm, and so in the absence of specification, this is the norm that we're going to be talking about. And this is just a distance formula, if you remember from your undergraduate math, measuring the distance between a point x and the origin. Only now our points are in this n-dimensional space. We probably only looked at them in something like a 2-dimensional space or a 3-dimensional space, where I have this point, AB, which in linear algebra, that becomes a vector, so it's pointed away from the origin and towards the point. And so I want to know the length of that red arrow right there. That's the vector x. And so I take the square root of a plus a squared plus b squared, just the hypotenuse of that right triangle. And in the distance formula, you're always subtracting the 2 points. And here the point, the origin is 0, 0. We'll see that in a minute. So there's really 2 reasons why we care about the length of a vector. First of all, we're going to want to make all vectors the same length in a number of applications. So this is a form of standardization, which you've already seen this in the statistical side of things, where Dr. LeVar talks about, standardizing variables to make them normally distributed with mean 0 and standard deviation 1, because it puts everything on the same scale. We're going to want to do the same thing in data mining, but we're not necessarily talking about normally distributed variables, and we don't care about standardizing them completely. We just want to normalize all the vectors to make them the same length. So we have to know how long they are in order to equate their length. The second reason is that the length of a vector, the length of the vector x minus y, will tell us the distance between x and y. So if I have 2 different points right here, x and y in blue, then the norm of x minus y will give me the Euclidean distance between those 2 points. And I can actually see that with vector subtraction. If I subtract y from x, I'm adding negative y, and I get this vector down here that's going to have the same length as this vector here. And so this is probably the distance formula that you may remember from a calculus class or even some high school math. The vector x minus y just takes the difference between the individual elements. And so I'm taking the square root, sum of squared differences between the 2 vectors. This is the Euclidean distance formula. All right, so let's look at an example. Suppose I have 2 vectors in 3 space. So x is 1, 1, 1, and y is 1, 0, 0. Then the magnitude of x, or its length, or the distance from the origin to the point 1, 1, 1, is simply going to be the norm of x, which is the square root of each individual element squared, added together. So square root of 3. Similarly, the magnitude of y is just going to be the square root of 1 squared plus 0, so that's 1. And then I can also find the distance between these 2 points. How far apart are they? Well, all I do is subtract y from x, which is what's happening in the parentheses here, square each individual element, add them up, and take the square root. So it's the square root of 2. Now this number here in this context, in this example, certainly doesn't tell me any information. I mean, it tells me how far apart they are, but I don't know, is that a far distance? It really depends on the context of the problem. And you might be thinking to yourself, well, in 3 dimensions, we could plot this data and we could look at it if I had more data than this. But the real thing here is that in reality, we have vectors that are not in 3 space, right? These observations have many, many variables, and we can't just look at them. And so we need these higher concepts of distance to tell us numerically what's close together and what is not. So one other thing I want to mention now, because we're going to make use of it regularly in the course, is the idea of a unit vector. So a unit vector is just a vector that has a length or a magnitude equal to 1. And so here are 3 examples, and these are these elementary basis vectors, or elementary vectors that we talked about before. 1, 0, 0, 0, 1, 0. These are the columns of the identity matrix, right? And these are all unit vectors because if I take their length, it's quite clear to see that if I square each element, add them up, I get 1, and take the square root of 1, I still have 1. And so these are kind of the simplest form of unit vectors. And so pretty early in this course in the fall, we're going to start with these specific unit vectors, and then we're going to start transforming our data using some other unit vectors. And that's basically principal component analysis. That's what it does in the background. So this slide, all I'm really giving you here is this terminology of a unit vector. And then next we're going to look at creating a unit vector. So if we have some random vector x, we can always transform it into a unit vector just by dividing every element by the magnitude of x, the 2 norm of x. So for example, if I have a vector that's 3, 4, well, we're going to make it a unit vector by dividing every element by the norm of x. So the norm of x is the square root of 3 squared plus 4 squared, which is 5. And so what I'm saying is the new vector, if I divide every element in x by 5, well, it's just multiplying x by 1/5. This new vector is a unit vector. So we can confirm that by looking at the norm of u, and I've done the math out here. 3/5 squared plus 4/5 squared is going to be 1. So this new vector, all I did was divide by the length of x, and that created a unit vector. And this unit vector is in the same direction as x, because all I did was scale x, right? I took a vector in one direction, and I shrunk it down so that its length is 1. And then just an additional note that when we have a unit vector, that's always going to imply that u transpose u is equal to 1, because u transpose u is just this, what's under the square root here. It's just the sum of squared elements. So that obviously must be equal to 1. Okay, so how else can we measure distance? So here are a couple of measures that pop up in almost every data mining textbook. We have the 1 norm, which is also called the taxicab metric, the Manhattan distance, or the city block distance. We'll show why in a minute. There's also the infinity norm, which can be called the max norm, the supremum norm, or the sup norm, or the uniform norm. And then the last one we'll talk about just briefly is the Mahalanobis distance. And so this is a probabilistic distance, and it accounts for the variance of variables. So we'll start with the 1 norm, that taxicab metric. So it can be called the city block norm, or the, like I said, the Manhattan distance, because what it does is it measures the distance between points along a rectangular grid. And so it's defined as the sum of the absolute values of the individual elements in x. So if I look at this vector here, I guess in green, or rather this distance perhaps in green, I want to know what the 1 norm distance is. So this is 2 dimensions, right? I have a x direction and a y direction, if you like. And so I'm adding up the absolute value of x and the absolute value of y. So I'm adding up how far I have to travel in the x direction plus how far I have to travel in the y direction to get to this point. So the red, the blue, and the yellow all depict ways that I can travel from this point to this point, but they all have the same distance because they all go up 1, 2, 3, 4, 5, 6 blocks, and they all go to the right. 1, 2, 3, 4, 5, 6 blocks. So 12 would be the Manhattan distance between these 2 points. This green line would represent more of a Euclidean distance. If I go straight from point A to point B, how far is that going to take me? So again, the one norm distance between two observations or vectors is just going to be the norm of x minus y. And again, this 1 has got to be there now to specify that we're talking about the one norm. We're not talking about Euclidean distance. And so it would be the absolute value of the difference between individual elements added together. Okay, next we have the infinity norm, and this is sometimes called the max distance, because the infinity norm of a vector is going to be the max absolute value of the individual elements in the vector. So it's the largest element in the vector in the absolute sense. And therefore, the max distance between 2 points or vectors x and y will be the maximum element-wise difference in those vectors. So you might start to ask yourself, well, when would I use the infinity norm or the 1 norm or the 2 norm? And it's really application specific. Again, I said, the 2 norm is by far the most popular, but depending on your data, there might be certain interpretations to these other distances that you like. Perhaps if these are, survey answers on a Likert scale of 0 to 10 between 2 participants, you want to know maybe what question did they disagree the most on and by how much. Or you might want the interpretation that comes with the 1 norm, like what's the total difference score between these 2 people. Whereas the square root sum of squares might be something that's a little harder for you to wrap your head around in terms of the application in the problem. So it really depends, but most often in data mining you're going to see that 2 norm distance. Another really nice distance formula is the Mahalanobis distance. And I'm not even going to give the formula here. It looks like a complicated linear algebra formula that deals with covariance matrices. You will see it again in data mining and probably in my class in the fall. And what it does is it takes into account the distribution of the data. Sometimes when you're comparing the distributions of different groups. So suppose here in this picture, I have one group of individuals, say it's alligators. And then another group of individuals here, and this is crocodiles. And they're being measured, it looks like, on 2 different variables. This is 2-dimensional data. And you can see there's a wide spread of how these variables relate to each other for the crocodiles. And then there's this relatively compact area where if you're an alligator, you belong in this region here. And so now say I have a new observation, this black dot over here with the question mark. Where should it go? Well, I don't know. I want to measure the distance, I suppose, between this new dot and maybe the averages of the other 2 groups. Well, how am I going to measure that distance? If I use Euclidean distance, this dot here looks like it belongs in the red group. I can see by looking at it that the trend of the blue group kind of points to maybe this belongs to the crocodile group. And so that's what the Mahalanobis distance will account for. It will account for the spread of the data. And this, brings up another point, which is largely what we're going to talk about in linear algebra is this directional variance. We talk about vectors and they have arrows and they point in directions. Well, why? Well, here's a good example. The variance of this data points in this direction here that I'm scrolling through with the mouse. Most of the variance is in this direction, and then there's some in the opposite direction too. Whereas in this red circle, I don't know, it looks pretty round. Maybe most of the variance is in this direction, but it's pretty equal in every direction. And so that kind of information can help us understand where or what the data looks like, especially when we're talking about higher dimensions. Okay, enough about that. One of the points I want to make is that, yes, this stuff is useful. We do a lot of notational stuff in this primer course, and a lot of times I have trouble convincing students that this stuff will all come together in the end, and you will be able to paint a much clearer picture of your data if you're able to understand the language of linear algebra. And I can't really do that until the end of the course when we know that language, and so I can present some very interesting techniques in that language. Happily, with distance, I'm able to show you an application right now, and it has to do with the recommendation system. So every time you go to Amazon, I'm sure you've seen products recommended for you, or Pandora, where they recommend songs. Those are recommendation systems. And so this website, Movie Lens, is a website that provides these non-commercial, personalized movie recommendations. So you create an account and you start rating movies that you liked or didn't like specifically. And they collect all your data and they use it to recommend new movies to you. And this was a part of a massive open source project to create recommendation systems. And the website releases large amounts of its data to the public so that they can play with it. And this is probably a data set that we're going to use in the fall. And one table that you can get from this data is looking at a user movie rating matrix. So I have a bunch of different users. We'll say these are their IDs, user 1, user 2, user 3. And then I have several movies. This is just to give you an idea of what the data would look like. And then there's ratings here of how this user rated each movie. Now, of course, every user hasn't seen every movie, so there's going to be lots of missing values in this table. What we're going to do in the next, or what I'm going to show you, actually treats these missing values as 0. And it'll be interesting to see, once you get your hands on this data, whether or not you can improve upon this very simple distance measure approach by taking into account these missing values. Okay, so what we're about to see is something that treats these missing values as 0 and then just computes the distances between the movies. So movies that are more similar or have the same users rating them in similar fashions will be closer together in distance. Their distance will be closer to 0 than movies who are either watched by completely different people or are rated very differently by the same people. And so we're going to go to this website right here, and this is done by a guy named Tim Chartier, who teaches at Davidson College, and he's a friend of mine and does a really good job with his MOOC courses, the massively open online courses, through edX, I believe it is. And if you Google Life is Linear, you'll find his courses, and they have some really interesting linear algebra applications on them. And so this is one that he does. And so all we're going to do, we're going to use his little app here rather than go to R and build this ourselves like we will do eventually. And we can choose between Euclidean or city block distance. So let's look at Euclidean distance right now. And we can choose a movie that we want to look at. So let's look at Star Wars. And you can either use a data set that has 100,000 ratings, or you can use one that has 1 million ratings. So let's use 1 million. And then we can actually get both of these distance metrics to appear. So let's do that. And so if we look at the movies that are closest, Star Wars is not in the 1 million. It's in the 100,000, I know that. then these are the movies that return as being most similar to Star Wars, just by Euclidean distance. And you can see that this is a pretty good list. Return of the Jedi, Empire Strikes Back, Little Raiders of the Lost Ark, some more Indiana Jones, Star Trek. So these look like they're actually pretty good recommendations for Star Wars, and that's just based on Euclidean distance. So let's try something else, something like, let's go Disney, Cinderella. And also, very good, Cinderella. We got Dumbo, Pinocchio, Snow White, a bunch more Disney movies. Bedknobs and Broomsticks, one of my favorites. And it doesn't seem to really matter whether you use Euclidean distance or study block distance. You do get different movies, perhaps in a different order, but they both work really pretty well. So you could play around with this, and you could try to find some movies where it doesn't work. I'm sure that there are some. I haven't looked around for one yet, but let's try Dracula. Oh. Okay, so that's something that you can do. So you can take a look at, and if you want to, you can download the data and start to play with it if you want some practice, but that's something we'll do in the fall. So that's all I wanted to show you today, and I hope that you all have a wonderful rest of the day or evening.